Hello everyone and welcome back to chapter 4. We're going to finish up today with sections 3, 4, and 5. As you probably recall, we are talking about probability and counting rules in this chapter. And the reason for that is because probability, the idea of randomness, is kind of foundational to statistical analysis. And so we kind of take this little sidestep into a different branch of mathematics and talk about statistics for 2 chapters, technically. Chapter 4 is definitely probability. Chapter 5 is also probability, but not the same type of probability. So the real heavy probability is here in chapter 4. And today we're going to be talking about, in section 3, the multiplication rule and conditional probability. So again, this is section 4.3. And our learning objectives are to find the probability of compound events using the multiplication rules. Now, compound events is when you have events that occur one after the other. So for instance, our example of drawing a ball out of a box and replacing that ball and drawing it again. So we talked about, what if you had a red ball and a blue golf ball in the box and you did 3 draws. So that would be a compound event because we're doing 3 draws and not just 1. The other thing that we're going to talk about is conditional probability of an event. And that means when we're talking about conditional probability, we're talking about probability based on something that's occurred prior. Okay, so based on prior event. So conditional probability, remember think about what the word conditional means. Conditional means like based on or because of, for instance, your people's health care, people's insurance might be a condition of their employment. So conditional means based on or because of. So when we're talking about conditional probability, we're talking about an event occurring based on what happened in a prior event. So let's start with multiplication rule 1, probability multiplication rule 1. So we first need to define what independent events are. And of course, if there's independent events, you can guess that we'll also be talking about dependent events. So if 2 events are independent events, that means that one event occurring doesn't affect the probability of the other event occurring. So for instance, if you roll a die and you roll it twice, if the first roll comes up a 5, that does not affect the likelihood that the second roll comes up 2. So once I've rolled a 5 on the first die, or anything, whatever I roll on the first die is not going to affect the probability of getting any other number on the second roll. So just because I roll a 1, or in this case it's 5, just because I roll a 5 the first time doesn't mean that the next roll, so this is roll 1, on roll 2, I still have a 1/6 probability of any number on the die occurring. I have a 1/6 chance of a 1, a 1/6 chance of a 2, a 1/6 chance of a 3, and so on. So the probability of rolling a 5 on the first die is 1/6. The probability of rolling a 2 on the second die is still 1/6. Okay, they would all be equal to each other. A lot of times you'll see this described as, and I like this description, is that the die does not have a memory. So the die does not remember on the second roll what it rolled on the first roll. the die doesn't have a memory of what happened. It just resets itself every time you pick it up. It's like a new die. So when you have that reset type of situation, then the events are going to be independent. And again, let me emphasize that just because you rolled a 5 on the first die doesn't mean you have less of a chance of rolling a 5 on the second roll. You still have a 1/6 chance. There's actually something called the gambler's fallacy, which is where a gambler will use the fact that they've lost as a justification that they must be going to win soon because there's no way they could lose again. So they believe that because they've been doing poorly, then they have to have a better chance of doing better after that. And that's how people lose a lot of money. Okay, so then if we look at another type of situation where we don't have something like a die, such as drawing a card out of a deck, you can still make those events independent, the consecutive events independent, if you replace the card. Okay, so it's independent if you replace what's been removed. So if you think about the blue golf ball and the red golf ball situation that we had in the prior sections, I specified very clearly that after each draw, whatever you drew went back in the box. Well, that was replacing and resetting the box so that each draw out of the box was an independent event. So replacement causes independent events. Okay. And if we have two events that occur one after another and they're independent of each other, then all we have to do is we have to take the probability of the first event happening times the probability of the second event happening. So let's think of our die here. So we were talking about 5 and then 2. So what's the probability that you're going to roll a 5 on the first die on roll 1? And then on roll 2, you're going to roll a 2. What's the probability of that happening? Well, the probability of getting a 5 on the first die, so I'm going to write it like this. So probability 5, 2. So that means 5, then 2. The probability of rolling a 5 is 1/6. And the probability of rolling a 2 is also 1/6. And so the probability of rolling a 5, then a 2 is 1 out of 36. 1 times 1 gets us the 1, and 6 times 6 gets us the 36. Again, if you are at all uncomfortable with the fractions, use your calculator, make sure you're getting the right numbers. But when you're multiplying fractions, you multiply across the top, multiply across the bottom. Don't have to have a common denominator with multiplication. And if we think back to I think I have one of these. Do I have a? I do not. Hold on one second. I'm going to pull up a sample space for 2 die. Okay, so this would be, the way they have this displayed here would be a sample space for rolling 2 die, like 2 die at the same time, but it's going to give us the same probabilities as if we rolled 1 die and then picked it up and rolled it again. So if we look on here, we have 5 and then 2 is occurring right here. Okay, and that is one way, only one way, out of the 6 times 6 or 36 total ways that you can roll the 2 die. 5 and then 2 is 1 out of 36 ways for the die to be rolled. Okay, so let's look at this multiplication rule with a couple more examples. So what is the probability of flipping a coin twice and first getting heads and then tails? Okay, so we want to know the probability of heads than tails. So what we're going to need to do, because these are independent events, because when we pick up the coin, it's just like the die, it doesn't have a memory of what happened the first time. So if we pick the coin up and we do an honest flip of it, we have just as much a chance of getting a heads or tails on the first time as we do of getting a heads or a tails on the second time. So we're going to take the probability of getting a heads on the first flip times the probability of getting a tails on the second flip. And so that would be a 1/2 chance of getting a heads on the first flip times a 1/2 chance of getting a tails on the second flip. And honestly, anything that you have would have this same probability, whether you said heads, tails, tails, heads, 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 or tails, tails. All of those have an equal chance of happening, and that would be a 1/4 chance, which of course would be 0.25 or 25%. And when we're using the calculator, we can put these in as fractions with a multiplication in between. So 1/2, and then we're going to arrow over so that it's out to the side of the fraction, times 1/2. And that'll get us 1/4. And again, if we want to switch it to a fraction, we do shift so we can get the F to D fraction to decimal. Change and hit enter, and that tells us it's 0.25. So anything you need to do with your fractions, you can do on your scientific calculator. So in this case, we have a spinner, and we want to know when we spin that spinner, what's the probability of getting first a red and then a blue. Okay, so we're going to look at the spinner, and the first thing we need to know is how many sections does it have. So 1, 2, 3, 4, 5, 6, 7. Oh, I've found another mistake with the slides. Let's cross this out because this isn't correct, because they had it as if it had 8 pieces instead of what it actually has is, we'll count them, 1, 2, 3, 4, 5, 6. That's halfway around. 7, 8, 9, 10, 11, 12. So there's actually 12 pieces. So the probability of getting a red then a blue is going to be the probability of a red times the probability of a blue, which is equal to how many reds, the probability of a red, well, there are 1, 2, 3, 4, 5 out of the 12 that are red. So 5/12 times the probability of blue. There's only 3 blue sections out of the 12, so 3 out of 12. So we're going to multiply those. Again, we're going to let the calculator do the bulk of the work for us. We could multiply that. We could, cancel, reduce the fraction and all of that, but not really that important for what we're working on. We can just do this on the calculator, and so we're going to get 3/12, which of course you could put in as 1/4. It's equivalent, times, hold on, I'm sorry, it's 5/12 first. Okay, so we want 5/12 times 3/12, which you could put in as 1/4. And then we're going to hit equals and let the calculator do the work, and that is 5/48. And if we want that as a decimal, that is approximately 0.104. Again, the 4, we're going to round that based on what's after it. There's a 1 after the 4, so we're going to leave the 4 alone, so it's 0.104. So 5/48 or approximately equal to 0.104 or 10.4%. Okay, so our last example of using the multiplication rule with independent events, and I didn't emphasize this on this one, but let's go back and emphasize it. with the spinner, as long as you're giving it a good spin, and the spinner is a fair spinner, it's not, you know, unlevel or something like that. If the spinner is a fair spinner, each time we spin that spinner, we have the equal chance of landing in any of these spaces. And so they are independent events. When we do a first spin and we get a red, that doesn't mean on the next spin that we have any more or any less chance of getting a red the next time. So they're independent events. That's why we can use the multiplication rule number 1, just the probability of a red times the probability of blue, because they're completely independent events. Okay, so now we're going to do a bag that's full of marbles. So we have a bag full of marbles, and I decided we were going to call these black, white, and zebra. And so the probability of drawing first a zebra, then a white, then a zebra. So zebra stripe, then a white one, then another zebra stripe one. This one is the first one that we've had more than just 2 events occurring. But we can use this multiplication rule for as many events as we have. So this would be equal to the probability of getting a zebra on the first draw times the probability of getting a white on the second draw times the probability of getting a zebra on the third draw. Now, we have to emphasize with this one, because we're using the multiplication rule 1, that the marbles are replaced between draws. Remember, we need it to either not have a memory, like the spinner or the die or the coins, or we need to replace it. So that the bag needs to be reset between each draw so that the events are independent of each other. So it doesn't matter on the second draw what you got on the first draw, because the bag's been returned to its original state. So the probability of a zebra stripe, you can see in here we have 1, 2, 3, 4 of the zebra stripes. Let me do that a little different way. I don't like the way that looks. So we have a zebra, zebra stripe, and another zebra stripe. There's 4 of those out of the total of 10 marbles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total. So 4 are what we want out of the 10. And again, yes, you could put that in as 2/5, but you don't have to reduce it until the end. Probability of white, once we have replaced this and we're back to our same 10 marbles, then the probability that we're going to get a white is 1, 2 out of the 10 are white. And so we're going to multiply that times 2/10. And then the probability of zebra, since again we've put these all back and it's replaced back to its original state, then the probability of getting a zebra stripe on the third draw is the same as it was on the first draw, because everything's been reset. So 4 out of 10. Okay? And so then, again, we just multiply this on our calculator. You don't have to do this by hand. You can if you want to. If you like doing fractions and you're comfortable with it, you can do it by hand. But if not, just type in your 4/10, arrow over, times 2/10, arrow over, times 4/10. Hit equals, and it will give you 4 over 125, which is the reduced answer. So 4 over 125 is your chances. So pretty low chance that you're going to get those 3 in particular. Only out of 125 draws, you would be expected to only have that happen 4 times. And then that is equal to 0.032, which is 3.2%. So only a 3% chance. So remember, percent means out of 100. So if you were going to draw 100 times, you would only expect that to happen just a little bit better chance of it happening 3 times or more. not 3 times or more, but there's a chance that it'll happen about 3 times. A little bit better than a chance of 3 times. Okay, so let's move on to our idea of dependent events. Now, when we're talking about dependent events, I want to emphasize that the multiplication rule is still in play. The only difference is that when we're looking at the consecutive events, the second event, the third event, if the events are dependent on each other, we have to take into account what happened on the first event, or prior events, however many there are. So if 2 events are dependent events, then the probability of B changes depending on what happened with A. And we then have what's known as conditional probability. So the probability of B / A means the probability of B given A has already occurred. Okay, so given that A has already occurred. So we're given that A has already happened, what's the probability that you're going to get whatever B is on the second one? So if we're thinking about drawing the marbles, if a marble's already been drawn out and we don't put it back in, that's going to affect the next draw, because there's not going to be 10 marbles anymore. There's going to be 9 marbles. So we have to take that into account. So if we think about drawing 2 cards from a deck of cards, and in this case, it's without replacement. And so without replacement means that they're going to be dependent events. Remember, replacing it makes them independent. So if we don't replace it, that means the chances on our second draw are affected by what happens on the first draw. So let's say the first card is a club. And the probability of getting a club is 13 out of 52, because each suit has 13 cards. And now I have a picture of this down here, so we'll go down and look at it. Okay, so here's our deck of cards. We have, in the deck of cards, we have 13 of each suit. So there's 13 clubs, 13 spades, 13 hearts, 13 diamonds. Okay, so we have a 13 out of the 52 chance of drawing a club. Okay, so let me get rid of all this so it's not in the way when we come back to it. But after we draw that first club out, then the next time there's not going to be 52 cards in there anymore. There's now only 51 cards. So if we leave that initial club out, there's only 51 cards. And not only that, but there's only 12 clubs. So the probability of getting a club, given that you've already drawn out a club, is 12 out of 52, because, sorry, not 52, 51, because we've removed one club on the first draw, and we've removed one total card. So we've removed one card, which has brought us down to 51 cards, and we have removed a club. So let's go look at our picture again, because I know a lot of people are very visual, and if you can see it, it makes it make more sense. So remember, we've already had one draw. So it doesn't really matter which club we draw, we just have to have drawn out a club. So let's say we drew out the 7 of clubs on our first draw. Now that that 7 of clubs has been removed, we don't have a total of 52 cards anymore. We now have only 51 cards because that club has been removed. So this one is gone and was not put back in. Okay, that one is out of there. Not only that, we don't have 13 clubs anymore. We only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 clubs now. So after we take that one club out, we only have 12 clubs out of 51 total cards. So the probability that we draw a club on the second draw, given that we've already drawn a club on the first draw, is 12 out of 51. And that's what we have to do with conditional probability when we're given something has already occurred with dependent events. And the reason that these become dependent is because we did not put that club back in. If we put the club back in, shuffled the deck, then you could say they were independent. But in this case, we're just going to draw that club out and we're not going to replace it. Okay, so the multiplication rule 2, says that if you have two dependent events, instead of just doing probability A times probability of B, you have to do the probability of A and then multiply that times the probability of B given A already occurred. So that slash bar right here means given, and then the second thing listed is whatever happened prior to that. So given that A happened. So in our case, probability of a club given a club already happened. So if we wanted to know, in this case, the probability of, let me slide this over so I have some room to write. So if we wanted to know the probability of getting a club and then a club, so not just each of those independently, but the overall probability of those two events occurring consecutively, we would have to do probability of a club times the probability of a club given that we've already drawn out a club. Well, we know the probability of a club on the first draw before anything's been messed with was 13 out of 52. And then the probability of a club given you've already drawn a club, we determined that that was 12 out of 52. And so this isn't really written on this slide, but just wanted to kind of, again, go a little bit above and beyond. So if we put that on the calculator, we have 13 out of 52 for the first draw. And then times 12 out of 52. And then if we hit enter, that's 3 out of 52. And then if we reduce that fraction, or if we change that to a decimal rather, we get 0.058. We have a 7 with a 6 after it, so that 7 is going to round up to 8. So 3 out of 52 or 0.058. Or 5.8%. All right, so let's look at our conditional probability in a couple examples. So the formula for conditional probability, which we already did a conditional probability, we did the club given a club, but the actual formula for this is the probability of A and B out of the probability of A. So using the formula, which I'm not going to emphasize the formula a lot. I'm going to show you the way that I like to give it. I like to give it in a table, kind of like I mentioned in the last section. But if you had the direct information and you needed to use the formula is the probability of B given A. So that's the second event occurring given that the first event occurred. So for our case, that was the 12 out of 51. If you needed to do a formula for that, you're going to take the probability of A and B happening out of the probability of A happening. So let's look at this example. It says, suppose 45 men and 55 women are asked if they've gone grocery shopping in the last week. 23 of the men and 41 of the women say that they have. So the probability that we have a woman shopper out of the entire sample is 41. So 41 of all the shoppers were women shoppers. So 41 out of 100. And then if we needed it, we don't need it in this case, but if we wanted to, have men shoppers, they would be 23 out of the 100. We end up not needing that, but we'll write it down. The other thing that we need is just the probability that one of the people is a shopper. So if you just picked a random person, what's the probability that they were a shopper? Well, in this case, there were 23 men shoppers and 41 women shoppers. So that is a total of 64 out of the 100 that were shoppers. And of course, if we needed non-shoppers, that would be the other 46 that were left. So for the formula, in order to get the probability that you have a woman given that you have a shopper, we're going to take the probability of woman shopper, which is this 41 out of 100, and we're going to divide it by the probability that they're a shopper, regardless of whether they're a man or a woman. So that'd be 64 out of 100. So we know from the prior example that we're going to multiply by the reciprocal. So that'd be 41 out of 100 times 100 out of 64. The 100s cancel and we get 41 out of 64. So if we wanted to do that on the calculator, let's do the division on the calculator. So let's say we had 41 out of 60, or out of 100 rather, and we wanted to divide that by the 64 out of 100. Then we get our 41 out of 64. And then if we want to switch that to a fraction or to a decimal, that's going to be 0.0641 because we want to round where the 0 is, and there's a 6 after it, so we're going to round the 0 up to 1, so 0.641. So this is approximately equal to 0.641 or 64.1%. But I really prefer to give this problem, and again, if you want to put, whenever I say something like this, I would put some sort of mark beside it. This is how I like to give the question on the exam. I like to give it as a table because I think it's more visual. I think we can kind of pull away from that, kind of plug numbers into a formula and try to really understand what we're doing. So I prefer to give a table. I'm going to start with this table with the formula, but then I'm going to show you the way that I would do it, staying away from the formula. So let me erase a little bit here to get some space. So we have the problem as the probability that we have a senior given that the student got to school in a car, gets to school on most days in a car. Okay, so probability senior given car. So the formula would say, what's the probability that they are a senior and they rode in a car? Divided by the probability that they're someone who gets to school in a car. Remember the second thing is the A. Okay. So in this case, the probability that they're a senior and came in a car, ride in a car most days, That would be 60 out of the 200. So again, that's the senior car riders. We want that they're both, okay? So senior and car. Now we're going to look at the bottom, which is the probability that they rode in a car. So the probability that they rode in a car is all the car riders, which is 80 out of 200. So if we divide that, we know the 200s are going to cancel, and we'll end up with 60 out of 80. However, this is not my preferred method of doing it. Let me show you my preferred method for when you have a table like this and you can really visualize it. Remember that this little bar in the middle here means given. So what we're saying is we want to know the probability that a student is a senior given only the car riders. In other words, we don't care about the bus riders, and we don't care about the walker bikers. We only care about the car riders. So that bar says throw out anything that's not after this bar. If it's not a car rider, don't even look at it. We don't care about them. We only care about the car people because we're given that they're a car rider. We're given only the car riders. So out of the car riders, the total is 80. And out of those, there are 60 that are seniors. So rather than doing this whole formula, cross out what you're not given. You're not given the bus riders. You're not given the walker bikers. You're only given the car riders. That gives you 60 out of 80. So you can see that from the table without going through this whole formula. And then 60 out of 80 is, of course, 3/4 or 0.75 or 75%. Let's do another example of that using my method. As I said, this is how I like to give it on the exam, so let's do another practice problem. So I'm going to do a whole different problem. Now, the given can either be the way that they get to school, or it can be whether they're a junior or senior. This one, the given happened to be the way that they get to school. But we can do it the other way. So let's do one, say, what's the probability that they rode the bus given that they're a junior? Okay, so remember that this means we're only given the juniors. Okay, so you could think of it as, let's say you had a bag full of chips, okay? And the chips were different colors. So let's say you had blue chips that were seniors, and you had red chips that were juniors, okay? And then on those chips, you could put that they rode the bus, that they rode the car, or that they walked or biked. Bus, car, walked or biked. And every student gets one of those chips inside of a bag. Red chip for all the juniors, blue chip for all the seniors, and then a letter on it for how they got to school. What we're saying when we have this given is that we're going to throw out all the blue chips. We're going to take that bag, we're going to upend it, we're going to dump all the chips out, and we're going to leave the blue ones out and only put the red ones back in. Okay, so all we have in the bag is the juniors. We're given only the juniors. Okay, so we don't care, in this case, anything about the juniors. Or I'm sorry, the seniors. We only care about the juniors. And so if we go over to the table, we don't care about the seniors because we're given the juniors. So we do not care at all about this row right here. This row is gone. We only care about the juniors. Okay? And out of the juniors, we're looking at the probability that they're a bus rider. So out of the juniors, which is 100, 70 of those rode the bus. So 70 out of 100, or 7/10, or 0.7, or 70%. So given that we're only looking at the juniors, there's a 70% chance that the junior that we draw out is going to be a bus rider. Okay, so we threw out this row because we didn't care about the seniors. We were only given the juniors. And then our total now becomes 100 because we've thrown out the 100 seniors and we're looking at 70. I had a student one time that said to me when they do these problems, they think of this bar as being like a fraction bar. So under the fraction bar, they put how many juniors there are in this case. And above it, they look at how many are junior bus riders, so 70. So they said, well, that bar to me looks like a sideways fraction bar, and the bottom number is the number of juniors, and then the top number is the number of the bus out of those juniors, which is the 70. And I thought that's a perfectly reasonable way to look at it. It is exactly true as to how it gets filled in. Okay, so let's move on to our these are actually two more examples of multiplication rule 2. So this is a deck of cards, but I'm going to do it similar to, well, actually, this is using multiplication rule 2 for consecutive events. So this is not exactly like what we were doing here. These were just conditionals. Okay, now we're going to be going to events that happen concurrently. So one event after another. So what is the probability of drawing an ace, then a king, without replacing the card? Okay, so we already did club, club. So now let's do ace, king. So we want to know the probability of an ace, then a king when we're drawing out two cards. And we are not replacing the card in this case. So we're not resetting the deck and shuffling it up. We're just doing one draw. We really should shuffle it before the second draw, but we're going to do the first draw, leave that card out, and then do the second draw. So in order to do this, we want to know the probability of getting an ace, and then we're going to multiply it by the probability of getting a king, given we already got an ace on the first draw. It's really the same as multiplication rule 1. We just have to take into account on the second one what happened on the first one. So the probability of getting an ace on the first draw, we have 4 aces. Okay, so that would be 4 out of 52. And yes, you could put that in as 1 out of 13. It's the same thing. So however you visualize it, I visualize it as 4 aces out of the 52. Then the probability of getting a king after you've drawn an ace, visually, that means one of these aces has been taken out. Okay, so I still have 4 kings. But the thing that has changed, the thing that makes this a dependent event, is I no longer have 52 cards. I only have 51 cards. So it's not 4 out of 52, it's 4 out of 51. A little bit different than the club problem because we're not drawing the same card twice. So the other problem was club, club, so we had to go from 13 to 12 clubs. But in this case, we haven't affected how many kings there are. We've only affected the total. So 4 out of 52 aces on the first draw. But once we've drawn out that ace, we still have 4 kings, but only 51 cards. And if we multiply that, this actually is a pretty small number. It comes out to be 0.006. If we change that to a percent, that's 0.6%. So the chance of drawing an ace, then not replacing it and drawing a king is less than 1% chance that that's going to happen. Less than 1 out of every 100. About 1 out of 200 times that's going to happen. Close to that. So if you want to see this on the calculator, that would be 4 out of 52 times 4 out of, well, let's do this with fractions. 4 out of 52 times 4 out of 51. And it will give us a fraction, but it's this really small fraction, 4 out of 63. And then, as I said, if we switch that to a decimal, it comes out to be 0.006. So we could say 4 out of 63, or we could 4 out of 663, or 0.006. All right, so one last example of multiplication rule 2. We're going to look at the bag of marbles that we had before. So we're going to do the exact same thing we did on the last one, but on this one, we're going to not replace. The marbles are not replaced between draws. So we're still going to do probability that we get a zebra stripe, then a white, then a zebra stripe, but in this case, it's not replaced. So first, we're going to look at what's the probability that we get a zebra stripe. So zebra stripe on the first draw is 4 out of the 10. Okay, but we're not going to replace that. And so when we go to do our second draw, one of these zebra stripes is gone. Okay, so now instead of having 10 marbles, we only have 9 marbles left now. So one of the zebra stripes was taken out, so instead of 10 marbles, we have 9 marbles. What about the white marbles? Well, we do still have 2 white marbles. So 2 white marbles out of the remaining 9. But now we're going to draw one of those out, so that one's gone. And so when we do the zebra stripe again, now we already took a zebra stripe out, so there's only 3 zebra stripe marbles, and there's only 8 marbles left. So when you're not replacing, each of these numbers on the bottom is going to go down each time. And then the number on the top is going to go down if we repeat something. So in this case, we had to go from having 4 zebra stripe marbles to 3 because we did a zebra on the first draw and then again on the third draw. So if we multiply those out, we're going to do 4/10 times 2/9 times 3/8, and we get 1/30 as the reduced fraction. 1/30, if we switch that to a fraction, to a decimal, is going to be 0.0333. Just like 1/3 is 0.333, the 1/30 gets a repeating 3 also. It's just from the 100th spot on. So 1/30 which is approximately 0.033 or 3.3%. So only a 1 in 30 chance that you're going to draw out of that bag without replacing a zebra, then a white, then a zebra. Now, is that better or worse than before? Well, without replacing, we actually get a better chance. Remember, before it was 0.032? So we actually have a little bit higher percentage when we're not putting it back because you've taken one of those zebra stripes out, so you have a little bit better chance on that second draw of getting a white. Only 2 out of 9 instead of 2 out of 10, or it's 2 out of 9 instead of only 2 out of 10. And so we end up with a little bit higher percentage of that happening than we did when we were replacing them. All right, so now we are ready for section 4. So section 4 of chapter 4. And we're still talking about probability, of course, and now we're going to actually talk about those counting rules that we've mentioned a couple times. So the counting rules, we're going to have 3 learning objectives. We're going to want to know the total, or be able to find the total number of outcomes in a sequence of events using the fundamental counting rule. And we also want to know the number of ways that R objects can be selected from N using the permutation rule, and the number of ways that R objects can be selected from N without regard to order. So permutation is going to be order matters when we draw the items, and then combination is going to be order doesn't matter. All right, this one's kind of hard to give you a heads up and kind of explain where we're going. We just need to go there. I'll show you what we're going to do. So the fundamental counting rule is how many different ways can something happen? So the fundamental counting rule in itself is just take the, I don't know where this L came from. Let me rewrite this off to the side. So this should be like K1 times K2 times K3 ... up to Kn. So what do we mean by that? Well, we mean that if we have 5 ways to do the first thing, then 2 ways to do the second thing, then 3 ways to do the third thing, we're going to take 5 times 2 times 3. Take a real simple example like being at a buffet at a wedding, let's say. So you're at the buffet at the wedding, and you can pick a main dish, you can pick 2 sides, and then you can pick a dessert, and then you can pick a drink. Okay, so say there's 3 main dishes. Let's say you can pick a beef option, you can pick a chicken option, or you can pick a vegetarian option. For the sides, you can pick green beans, you can pick mac and cheese, you can pick, what did we say? Let's say 5 sides. So green beans, mac and cheese, rice, corn, or you can pick mashed potatoes. Okay, and then for a dessert, there's some apple pie, or there's some chocolate cake. And then for drinks, you have tea, water, lemonade, or coffee. Okay, so how many ways can you pick your plate at that buffet? Well, if we look at each item, out of the mains, you have 3 things that you can pick. Out of the sides, you have 5 things that you can pick. Out of the desserts, you have 2, and out of the drinks, you have 4. So if we multiply those using this property that says we're going to have how many ways you can do the first thing times how many ways you can do the second thing times how many ways you can do the third, all the way up to the last thing. Well, in this case, if we pick a main dish, we have 3 different ways to do that. And then we said we were going to pick 2 sides. So we have side and then side. And then we have dessert. And then we have drink. Okay, so sides, this is going to be 5 for certain for our first side. And then now we have to ask a question. For the second side, can we pick the same thing? Could I say, I want 2 servings of mac and cheese? Because who wouldn't want 2 servings of mac and cheese, right? So do we want mac and cheese? Can we do that? Or do we have to pick a different thing? So let's say we're not allowed to pick the same thing. Well, that means after we make this first side choice, say we pick mac and cheese, now we only have green beans, rice, corn, and potatoes to pick from. So our second side would only be 4. So again, that would be dependent. What we pick on the second one is dependent on the fact that we couldn't put that first one back. Desserts, we have 2 choices, and then our drinks, we have 4. Now, if you multiply that out, 3 times 5 times 4 times 2 times 4 again, you will be amazed at how many different ways in just a small buffet, this isn't even a very elaborate buffet, there are 480 ways to pick your meal with your dessert and your drink. So 480 different combinations that you could make with 3 main choices, 5 sides, 2 different sides, a dessert, and a drink. So if you wonder why, the person sitting next to you very rarely has the exact same things that you have, because if things were random, there's only a 1 in 480 chance that they're going to have the exact same thing as you. So that's a quick example of the fundamental counting rule. Let's look at another one. So this one, they're using coins that we're going to flip. So it says, suppose a coin is tossed and then a die is rolled. How many outcomes are there for this? Well, they've got their tree here. They have heads and then tails. And then off of that, once they've done the coin, then they say, well, for the die, I could have 1, 2, 3, 4, 5, or 6, giving us heads with a 1, heads with a 2, heads with a 3, and so on. And then if we do the same thing with the tails, we could do tails with a 1, tails with a 2, and so on. So there's 2 ways to flip the coin. It's kind of like our 2 desserts, times 6 ways to roll the dice. So 2 ways to flip the coin. Each of those has 6 ways to match with it to roll the dice. We get a total of 12 possible outcomes. For just flipping a coin and rolling a die, there's 12 different ways that could happen. Again, heads with a 1, heads with a 2, all the way through 6. That gives us 6 with the heads. And then if you could have a tail with any of those die rolls, you'd have another 6. So 2 times 6, we have 12 different ways that could happen. Now we're going to do factorial notation, but this is kind of a sidestep to what we ultimately need it for. But we need to know what factorial notation is. So factorial notation is if you have, say, 5 cards in a pile, and we're going to draw each one out without replacement. The number of possibilities for your first draw are 5. So your first draw, there's 5 different cards you can pick from. For your second draw, since you haven't put that first card back, you only have 4 ways. For the third draw, you only have 3 ways. Think of it like the mac and cheese. Once you remove one of the mac and cheese, once you remove the mac and cheese, you only have 4 other sides to pick from. Once you remove one of those cards, then you have 4 cards, then you have 3 cards, then you have 2 cards. And then at the end, if you knew what the first 4 cards were, you would know what the last card is because it's the only one left. If you had 7 cards in the pile, it's going to be the same situation. It's just going to start, the first draw is going to start with 7. The second draw is then only going to be 6, and so on until we get down to 1 again. Okay. Now there's a special name for this process of starting with an integer and multiplying down until the end. It's called a factorial. And the symbol that we use for a factorial is a multiplication, or not a multiplication, an exclamation point, interestingly enough. And so, why is it an exclamation point? Go back a little history here. The reason that it's probably an exclamation point is because when this was first developed, someone would have been writing a math book. They would have said, I want to define this new symbol, mathematical symbol. But at the time, they had printing presses, and they had little blocks that they had to set in the typeset. And if they would have used a symbol that wasn't already there, it would have had to have been developed. So they said, well, what symbol can I use that's not already used in mathematics, but would be available to the typesetter? And so they said, well, let's use an exclamation point. That's not used anywhere else in math. Let's grab that. So just kind of an interesting side note. This also should not be an L. For some reason, this slide looks like whenever somebody entered ... it gave an L for some reason. So n factorial means start with n, then do 1 less than n, then do 1 less than that, and all the way down until you get to 1. So in our case, this would have been our 7. 1 less than 7 is 6. 2 less than 7 is 5. And then you would keep going until you got to 3 times 2 times 1. Also, we have to define 0 factorial because our factorial stops when we get to 1. It wouldn't fit into the normal definition of what a factorial is. So we have that defined in a little bit separate way. A 0 factorial is actually defined as being 1. And the reason that that happens is you could think of it as if you had no cards in the pile, how many ways could you possibly pick that out? Well, there's only one way you can pick it out because there's nothing there. And so that fits into what we need for the definition of the factorials. So the factorials on your calculator, on most calculators, there's going to be a separate button somewhere that has a factorial symbol on it. So on this calculator, it is actually under another button. And sometimes that's the case, and sometimes it's just like above a button or on a button. You will just have to look on your calculator. If you have any questions, if you can't find it, you can try to Google it. You could also email me if you get really stuck. But on this particular calculator, like a lot of calculators, it's actually under this PRB for probability button. So we're going to hit, if we want to do 7 factorial, we would do 7. And then we would hit probability, and we would go down and select the exclamation point looking symbol. That would give us 7 factorial, and then we would hit enter. So 7 times 6 times 5 times 4 times 3 times 1 is 5,040. Let's go through that again. So if we hit 7, then the PRB button, arrow down to the exclamation point, or we could push 3, but I like to arrow down. Enter, and then enter again, and we get 5,040. If we wanted to do 5 factorial, 5 PRB factorial is 120. But the factorials are going to be a means to an end. We're not really going to use those directly very much. What we're going to use factorials for are for permutations and combinations. And of the two, the most important thing with these is that permutations, the order matters. And with combinations, the order does not matter. And the way I remember this is kind of strange. You can come up with your own way to remember it. But in order for the combination, I always remember that combination, when we think of in everyday language, if somebody said combination, fill in the blank, you might say combination lock, you know, like your master lock on a locker or something like that. Well, combination locks are named entirely wrong. Combination locks, first of all, the order does matter on a combination lock, or what we call a combination lock. And also you can repeat numbers on a combination lock. So you could have a combination that was like 10, 27, 10. So you can repeat things. And with permutations and combinations, you can't repeat things. And so combination locks are named entirely wrong. Because with a combination, you can't repeat things and the order does not matter. Permutations, the order does matter. Remember it how you want, but that's the crazy way that I remember it. So a permutation is an arrangement of n objects when the order matters. So let's say we had 4 people in line for a family photograph. The first person in line, we could pick any of the 4 people. So we have 4 ways to pick that first person. And then for the second person in line, once we've placed that first person, we have 3 people we could choose for the second spot. And then for the third spot, we only have 2 people left. And then for the last spot, we've only got 1 person left. So we could say there's 4 times 3 times 2 times 1, or we could calculate that as a 4 factorial. We'd get the same thing. So that comes out to be 24. So there's 24 with just 4 people in a photo. If you're putting them in a row, there's 4 times 3 times 2, or 24 different ways to arrange them. Again, if you're standing trying to get a photo taken and people can't agree who should stand where, there's 24 different ways for that to happen with just 4 people. Let's say you're going to do something similar where you have 20 students in a class and you're going to select 3 of them to fill roles. So not just select 3 of them, but you're going to actually put them in a role. Say you're going to have a president, a vice president, and a secretary. Well, for the president spot, get rid of this. In this case, the order matters. And so we have 4 ways to pick the first person. I'm sorry, not 4, 20. So to pick the president, we have 20 different people we can pick from. To pick the vice president, we now have picked one of those people out, so we have 19 people left for vice president. And then if we say secretary, we have 18 people left to pick for the secretary. Now, if you multiply 20 times 19 times 18, that's 6,000 in just a class of 20 students. That's 6,840 ways to fill those 3 seats. Kind of unbelievable. Now, this is where we're going to lead into how we calculate a permutation. That calculation, that 20 times 19 times 18, if you were to write that as 20 factorial over 20 minus 3, because there's 3 spots. So 20 minus 3 factorial, you would actually get the same thing, because the top is 20 times 19 times 18 times 17 times 16 and so on until we get down to 2 times 1. And then the bottom is 17 factorial, which would be 17 times 16 times 15 all the way down to 2 times 1. Well, if I cancel, with fractions I can cancel like factors on the top and the bottom. That means on the top I could cancel all the way from 17 down to 1, 17, the 16, the 15, and so on, with the 17, 16, 15 on the bottom. So this right here, 17 down to 1, is the same as this 17 down to 1. So I can cancel those. Well, look what I'm left with. I'm left with 20 times 19 times 18. And so we could call permutating 3 objects out of 20 objects, or in this case 3 people out of 20 people. We have a special name for that. We call it 20p3, which is equal to 20 factorial over 20 minus 3 factorial. In general, if you have n objects and you're going to permutate 3 of those objects, then it would be n factorial on the top and then n minus r. So in our case was 20 minus 3. If it's n and r, just in general, it'd be n minus r. Now, I'm going to show you how to do this on the calculator, because I want you to understand where it came from, but in practice, you are welcome for this calculation to just do it on your calculator. Okay, so your calculator will do a permutation. You may have noticed when we were doing it that there were a couple other things under the PRB button. So if I want to do this 20p3, I first type in the 20, then I hit the probability key, and you can see the first one is NPR. I'm going to hit enter, and then the 3, and hit enter again. So 6,840. It's the same number that we got before. Okay? So on your exam, what I want to see is if you see a problem that says, you know, say your problem is, what if we had a class of 20 students and select 3 of them to fill roles? How many ways are there to arrange them? I would want to see on your, for your work, either 20 times 19 times 18, or you 20p3, and then just hit enter. After that, 6,840. And then I know that what you did is you went on your calculator and you calculated 20p3 on your calculator, so you knew it was a permutation, which meant you knew that the order mattered. You knew that there was 20 that you were selecting from and 3 that you selected, and you put it into your calculator correctly. So this would be all the work that you would need to show on an exam, a written exam for this. Okay, so again, the key things for a permutation is you can't put things back in. When you place an object, that object is out, so there's no replacement. And then also the order matters for permutations. Now, if we go to combinations, it's the same situation, but with combinations, the order does not matter. Okay, so we have combinations, order doesn't matter. So let's look at a simple example. Let's look at the letters A, B, C. So if you have A, B, C, for a combination, that would be the same as A, C, B, because the order doesn't matter and you have the same 3 letters. That would also equal BAC, would also equal BCA, would also equal CAB, would also equal CBA. So all of these in a combination would be counted as just one thing. Whereas with a permutation, these would be 6 different things. Okay, so if you're talking about a P, a permutation, that's 6 different ways. But if you're talking about a combination, this is only one way. This is only one combination of the 3 letters ABC. Doesn't matter if it's ABC, CBA, BAC, you still have the same 3 letters. So for combinations, it's 1. For permutations, that would be 6. So when we're doing combinations, we actually get smaller numbers. Now, the formal way to calculate this would be NCR is n factorial over r factorial, n minus r factorial. So if we're looking at this next example, suppose we want to choose 2 t-shirts from your 8 clean t-shirts to pack for a trip. Now, why does order not matter? Well, you're not deciding what days you're going to wear those t-shirts or anything like that. You're just selecting 2 t-shirts to put into your bag. Okay, so you don't care whether you pick the yellow shirt then the white shirt or the white shirt then the yellow shirt. They're both going to be in your bag for your trip. So the order doesn't matter. So it's going to be a combination. So we have 8 things that we're selecting from. Choose 2. Combinations are usually referred to as choose. 8 choose 2. And the calculation for this, if you did it by hand, is 8 factorial over, you do 8 minus 2 again, like we did with the permutation. So that's 6 factorial, but then we also put this number of things that we're choosing out of there as another factorial. So for this, if we did it by hand, which again, you don't have to do it by hand, but I just want to show you how it's calculated. So this would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. On the bottom, we would have 6, 5, 4, 3, 2, 1. And then we'd also have 2 times 1 for the other factorial. So on top, everything from the 6 down would get canceled with this 6 down. And we would have 8 times 7 on top, just like we would with the permutation. However, we're going to divide that by 2 in this case, which is going to make a smaller number. So for a permutation, 8p2 would be 56, but with a combination, we're going to divide that by 2 times 1 and only get 28. Now, how do you do that on your calculator? The same way we do with a combination. It's almost always right nearby wherever you found the permutation to be. The combination is going to be right nearby. So 8 on this calculator, PRB, C is the next one down, hit enter, then our 2, hit enter, and you'll see it comes out to be 28. So hit how many you're choosing from that you want to do a C, a combination, and then how many you're choosing out of those 8 as your second number. All right, so let's say we had 20 students and you want to pick 3 representatives to go to the college council. Now that sounds very similar to what we had before, but remember when we were talking about it before, instead of just 3 representatives, we actually had positions. We had president, vice president, and secretary. So the order mattered because being chosen to be the vice president is different than being chosen to be the president, is different than being chosen to be the secretary. So when you're talking about actually putting things into a particular title or position, then the order matters. But in this case, we're not doing that. We're just picking 3 representatives to go. So it doesn't matter if you're picked first or second or third, you're still going to go represent the class if you're selected. So the order doesn't matter. Think of our ABC up here. So if students A, B, and C get selected, it doesn't matter who got chosen first, who got chosen second, who got chosen third. Any of these different ways, from ABC down to CBA, are still going to have the same 3 representatives. So the order doesn't matter. And in order to do this on your calculator, you're just going to do 20 C3, and that comes out to be 1,140. So 20 C3 is 1,140 ways. And remember when we did that with a permutation, that came out to be 6,840. So there was a lot more ways to do that when you were putting people into positions versus just selecting them to represent. Sometimes when we're doing a combination or a permutation, you have some things that are repeated. So, got that darn L here again. That should be dot, dot, dot. So this should be n factorial over r1 factorial, r2 factorial, dot, 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 rp factorial. So if we have identical objects within our combination or within our permutation, we not only have to do how many we're selecting, we have to take into account the fact that, for instance, in this word Toronto, if we're going to try to make as many permutations of the word Toronto as possible, that there are 3 O's and there's 2 T's that are identical. Okay, so if we're thinking of words, any of those O's are the same thing, and either of those T's are the same thing. So in order to do that, for the 7 letters, we're going to do 7 factorial, and then on the bottom, and of course, if we're talking about how many permutations, that means we care about the order. There's really only one combination of the word Toronto, because picking those 7 letters is picking those 7 letters. But if we're talking about a permutation and we care about the order, there's 7 factorial ways to place those letters, but we have to then divide out the fact that 3 of the O's are the same and 2 of the T's are the same. And so this might be the case. I would probably, in fact, I'm not even going to say probably not. I won't put one of these on your exam. I'm going to put just a permutation or a combination on your exam. However, you will run across some of these on your homework. So on the calculator, you're going to have to go ahead and use the factorial button. And so you're going to do 7 factorial. And I'm going to do it as oh, it doesn't like that. All right, divided by parentheses 3 factorial times 2 factorial. And you notice I put the bottom of that in parentheses so the calculator knows I want both the 3 factorial and the 2 factorial under the division sign. Hit enter and I get my 420. And then if we were going to do that repeat that with the word Mississippi, you can tell there's so many more letters in that. There's likely going to be a lot more permutations, and there are. There's 11 letters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 total letters. But then we have the S's repeated 4 times. So we need a 4 factorial. We have the P's, or the I's repeated 4 times. And then we have the P's repeated twice. So we have to put all of those under there. Anything that's not a repeat, we don't have to put in there. So in this case, the M isn't repeated, etc. So we have 4, and then 4, and then 2. And if you were to enter that in the calculator the same way, you would get 34,650. Different ways to permutate the letters in the word Mississippi. Unbelievable. I mean, that 34,000, more than 34,000 different ways. And so just to see that on the calculator really quick, again, you would do the 11 factorial, and then you would have to divide, and you need to put a parentheses on the bottom so that it knows everything that you're entering after that is underneath the division bar. And then you would have your 4 factorial times 4 factorial times 2 factorial. And there's your 34,650. All right, and then the last thing, I left this slide on. I don't usually leave up the TI-84 stuff, but because I have specifically said it's okay to do these permutations and combinations on your calculator, I just wanted to show really quick where you could find those if you have a TI-84 calculator. So if you have a TI-84 calculator, the button that you find your factorial and your NCR and your NPR under, you have to push the math button first. So push math, and then it'll look a lot like what we were doing. Okay? You push the math button, which is right here. Oops, why is it not letting me? Hold on. Okay, so the math button is right here, that red one that's lit up on this slide. And then, but before that, you push the 6. So like, let's say you wanted to do a 6P3, then you would put in 6, then you would push math, and then under math, you would pick NPR. So you arrow down to it, hit enter, or you can choose 2 since it's the second thing. Hit enter, and then put in your 3 and hit enter. And for a C, same thing. If you wanted to do 10C3, for instance, you would put in 10. You would hit the math button, which is this one over here, and then you would choose NCR from your drop-down menu, which is the third one. Then you would put in your 3, and then you would hit enter. All right. And remember, on your calculator, if you ever can't figure something out, you're welcome to ask me, but you also should be able to find pretty much anything these days. You should be able to Google it. Just put in the type of calculator that you have. So for instance, if you have a Casio FX115ES, which I have one of those, just type in permutations on Casio FX115ES. And you should be able to find either a picture or a short video on how to do that. Now on the Casios, I will say that the NPR and the NCR are not under a PRB button. They're, on this one in particular, the P is above the multiplication symbol, so I have to hit Shift to get it. So I would hit like 6, Shift, then the times button, then a 3 if I wanted to do a 6P3. Okay. I wish I had a way to show you that, but Casio doesn't have one online like the TI does. All right, so let's finish up Chapter 4 with Section 4.5. And in Section 4.5, we're going to kind of pull everything together. So we did probability, we did counting rules. You notice in Section 4.4, we didn't do any probabilities, we just counted things. But knowing how to count things helps us figure out the probabilities, because remember, we always have to know what's the number of total things and then what's the number of things that we want. And so we're going to take those counting rules and combine them with the probability rules, and we have more problems, types of problems that we can do. So Section 4.5 is just kind of pulling those together, find the probability of an event using the counting rules and, of course, what we already knew. So just a reminder, as we start Section 4.5, of just the general idea of probability. So, as we recall, the general idea of probability is that we need to figure out on top the number of ways to successfully get what we want. So here we're calling that event E. So how many ways can we successfully get whatever we're looking for as the probability. So for something simple, if we're rolling a die, we might want, what's the probability of rolling a 5? 5 would be our event. And then on the bottom, we need to know the total of all possible outcomes. So if we're thinking about a die, we've got 6 sides to the die, so there's 6 possible outcomes. So one way to get a 5, one way to get to successfully roll a 5 out of 6 total ways. Now, knowing the probability rules and the counting rules helps us determine these 2 items. So we're going to look at this first one. We won't use permutations and combinations yet, but we will on the next one. So, and this section is basically just 4 examples using what we've already learned. So we have a lottery game, not a big lotto game because it's only 3 numbers, but in this lottery game, you can select 3 digits, or 3 numbers are selected for the winner. And the digits are 0 to 9, and repeats are allowed. We want to know what's the probability that we get all 3 of those digits the same. Okay. So what we need to figure out first is how many ways can we get 3 the same? So what do they mean by 3 the same? They mean like 0, 0, 0, or 1, 1, 1, or 2, 2, 2. And of course we can do that with any digit all the way up to 9, 9, 9. So how many ways is that? Your first instinct might be to say that there's 9 different ways, but 1 to 9 is 9 different ways, and we're including 0. So there's actually 10 different ways that we can get 3 the same. So 1 to 9 plus the 0, 0, 0. So our top number, the number of ways to get 3 the same, there's 10 ways to do that. And then what about the bottom number? There's various different ways we could do this, but let's do it as if we're doing the multiplication rule from the last section. If we have the first digit has 10 ways to be selected, 0 through 10, or I'm sorry, 0 through 9. And then the second digit has 10 ways to be selected. And the third digit has 10 ways to be selected, because remember we can repeat, so these don't go down. It's just 10 possibilities each time. Then we're going to have 1,000 ways to select 3 digits. Got an extra 10 on this slide here. Let me cross that out. So 10 times 10 times 10 is 1,000. So if we reduce that, that would be the same as 1 out of 100, which is 0.01, 1/100th, or 1%. Remember, percent means out of 100. So if we have 1 out of 100, that's the same thing as 1%. So in this one, we used the counting rules, but we didn't use permutations and combinations. We used the 10 times 10 times 10. You could also think of it as just counting how many numbers are there from 0, 0, 0 up to 999, and that would be 1,000, because it would be 001 up to 999 would be 999 ways plus the 000. So however you can get that, we need to know that the bottom number is that there's 1,000 different ways to pick 3 digits. Okay, so now let's do some that involve our permutations and combinations. So let's say a class of 20 is conducting a random drawing for 3 people to be class president, vice president, and secretary. So kind of drawing off of what we did before, but now we're going to calculate the probability rather than just counting. So you would really like Xavier to win as president, Yelena to win as vice president, and Zenith to win as the secretary. What is the probability, if those are just 3 students out of 20 in the class, what's the probability that you get your wish? Well, the probability, or the number of ways to get what you want, is just 1. Okay, there's only one way to get what you want. You want specifically Xavier to win president, Yelena to win vice president, and Zenith to win secretary. There's only one way for that to happen. But how many ways are there to select those positions? To select the 3 positions. Well, we did that before, and we said because the order matters, because there's actual placements for them, it's not just 3 people that are going to go represent, they actually have jobs, a specific person for president, a specific person for vice president, specific person for secretary. If we have those 3 people but they're in different spots, that's a different selection. So out of those, the order matters, and so we have 20 students, and it's a permutation because order matters, and we're going to choose 3. And we found out in the last section that that was 6,840. So if you have one way that you want this to happen, your chances of that happening, if it's just a random selection rather than people voting or something like that, you're just drawing names out of the hat, first name out, that's the president. Second name, that's the vice president. Third name, that's the secretary. If it's just a completely random selection, you only have a 1 in 6,840 chance of that happening because there's 6,840 ways to draw those 3 names. If we try to switch that to a decimal, that comes out to be 0.0001 or 0.01%. Much smaller than 1 in 100. Again, it's 1 out of 6,840. If we look at that on the calculator, you can see, remember our rule was that we can go to the first non-zero digit if we have something that's really small. So 1 divided by 6,840 is 0.000146,199. And we can go, if we're going past 3 digits, we can go to the first non-zero digit, which is the 1. So 0.0001, which is approximately, which is 0.01%. Okay, so now let's change the situation as we did in the other section. What if we're still, in this case, doing a random drawing? So nobody's voting on anybody. We're just randomly picking them. We still have 20 students in the class, and we're still going to have 3 people, but they're just going to be class representatives. So everybody has the same spot. You either get picked or you don't get picked. It doesn't matter what order you get picked in. So if you still want Xavier, Yelena, and Zenith to win, that's still one way to get those 3 people. Because remember, X, Y, Z, Xavier, Yelena, Zenith is the same as X, Z, Y, etc. Okay? It doesn't matter what order we pick them in, but there's still just one way to pick them, those 3 people. So there's one combination. And then on the bottom, because the order doesn't matter, instead of doing a 20P3, we're going to do a 20C3. And that gives us a 1 out of 1,140 chance, which when switched to a decimal is still very small, but it's not quite as small as what we had before. It's 0.0009 instead of 0.0001, which is 0.09%. Still way less than 1% because it's 1 out of over 1,000. 1 out of 100 would be a 1%. So it's still a very small chance that you're going to get all 3 people that you want, but it's a higher chance than if the order matters. So you can see we've combined our counting, permutations and combinations from section 4.4 with what we knew about probability. All right, so now we have, boy, we're stuck on the number 20 on these examples. A box contains 20 light bulbs, 4 of which are defective. So let me redo that since it kind of covered it up. So we have 20 light bulbs total, and we have 4 of them which are defective. If you're going to pick 5 bulbs randomly out of the box, what's the probability that exactly 2 of those are defective? So in this case, the order doesn't matter, because it doesn't matter if we get the defective on the first and the second, or the first and the third, or the first and the fourth. We're just looking for 2 defective anywhere in the selection. So what we do with this type of problem is we split it up into the 2 parts. So the number of ways to get what we want for the non-defective, actually let's do the defective first because that's how it's in the example. So the number of ways to get defective, we want, out of the 4 defective, we want to have 2. Order doesn't matter, so we're doing a combination. Then we have the number of ways to select the non-defective, the good bulbs. Well, there are, out of those bulbs, remember 4 are defective, so that means that there's 16 good, 16 that are non-defective. So we have 16 that are non-defective, and out of those 16, we want 3 of them. Now, where did I get the 3? Remember, we're taking 5 bulbs total. So we have 2 and 3 get us the 5 that are drawn, and then the 4 and the 16 are the 20 total. So we have 4 plus 16 to get our 20 total, and then the 2 and the 3 to get the 5 drawn. And out of the 5 drawn, we want 2 defective, and we want 3. We want 2 that are defective and 3 that are good, out of the 4 that are defective and the 16 that are good. Now that becomes what we need for our top number. So if we calculate these, that would tell us how many ways we have each. So the first calculation would be 4, choose 2. That's 6 ways. So the 4 choose 2 is 6. And the 16 choose 3 gets us 16 choose 3, we get 560. So if there's 6 different ways to pick the 2 defective ways and 560 ways to pick the non-defective bulbs, then there is a total of 4 choose 2 times 16 choose 3, or six times 560. So this is the probability of getting what we want, 2 defective and 3 good. Then on the bottom, we need to do the possibilities, the number of ways to just pick 5 bulbs out of the 20. So all 20 bulbs, choose 5. How many ways could you do that? Well, if we put that in the calculator, that comes out to be 15,504. And then if we type this into the calculator, let me see if it'll let me. Sometimes it'll let us put 6 times, yes, this calculator will let us put a multiplication up there on top. Okay, so 6 times 560 over 15,504, if we hit enter, that gives us 70 out of 323, which then, as a decimal, is 0.217. Okay, so here's our answer for that. We've got 70 out of 303, which is approximately 0.217. I've kind of run out of room over here, which is equal to 21.7%. And I just paused and looked because that didn't sound right to me. That's not supposed to be 303. That's supposed to be 323. That's what we got when we just computed it. Okay, so this reduces to 70 out of 323, not 303, 323. So 70 out of 323, which is about 0.217, which is 21.7%. You make that look a little nicer. Okay, so we think we have one more slide. Yes, we do. And we're going to look at the probability of getting a 4 of a kind. So suppose we draw 5 cards from a deck. We're just talking about a regular deck of cards. Again, if it helps you to have an image of a deck of cards up while you're doing cards problems, please do that. I would always provide it to you on the exam. And so I'm going to cross out this word identical because we can't get 4 identical cards out of a deck of cards. But we can get 4 cards that are the same rank. Meaning they're all 2, there's 4 2s or there's 4 3s. So when we say getting 4 of a kind, we mean 2 2 2 2, 3 3 3 3, jack 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 jack. Okay, so out of those there are 13 ways to do that. So if we list them out, we can get 4 aces, we can get 4 2s, we can get 4 3s, all the way up to 4 jacks, 4 queens, or 4 kings. So there are 13 ways to get 4 of a kind. After that, there are 48 other cards left. So once we've drawn out 4 cards from our deck of 52, let's put up a deck of cards here so we can visualize it. So once we've drawn our 4 of a kind, whatever it may be, let's say we get 4 5s. Well, the 4 5s are gone for our 4 of a kind. And then because we've taken out those 4 cards, instead of a total of 52, we now have a total of only 48. We have 12 left in each suit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we only have a total of 12 remaining in each suit for a total of 48 that are left. So we have 13 ways to get our 4 of a kind, from all aces to all kings, and then we have 48 ways to pick that remaining card. And the order doesn't matter. We're just talking about a hand of cards. It doesn't matter which order they were dealt in. So our top number is the number of ways to get a 4 of a kind. And then the bottom number will be the number of ways to draw 4 cards out of a deck of cards. to draw 5. Okay, so on the top, we have 13 ways to get our 4 of a kind times our 48 cards left. So we could have a 5 to make our 4 of a kind, and then ace of clubs. Or we could have those cards with a 2 of clubs. Or we could have those cards with a 3 of clubs. We could go through that. There's 48 different things you could put with the 5s. And then remember, there's not just that one way to get the 4 of a kind. The 4 of a kind could be the aces, the 2s, the 3s, the 4s. So there's 13 ways to do that, times the 48 cards that would be remaining. And then the number of ways to draw 5, that's a lot easier to compute. We have 52 cards. Order doesn't matter, so we're doing a combination. So 52, choose 5. And that top number comes out to be 624. The bottom number comes out to be 2,598,960. And then that reduces to, double check that on the calculator, since we have found a couple mistakes. I don't want anybody to get confused. So 13 times 48 gets us the 624. And then we have so many cards here that we're going to get a very large number for our combination. 52, choose 5, gets us that 2,598,960. Okay, so if we put that into the calculator as a fraction, we get 624 over 2,598,960, which reduces to 0.0002, because we're going to stop at that first non-zero digit, or let's see if it'll give it to us as a fraction. I'm sure it will. Oh, nope, it doesn't like that as a fraction. So we'll just have to take the word of the textbook, or the textbook slides, that comes out to be, yes, that's 1 over 4,165. That's because 2,598,960 must be divisible by 624, which it is, 4,165 times. So that's how we get the 1 out of 4,165. But this calculator didn't like that. It said that's too big of a number in a fraction. Let's just switch it to a decimal. So in ALEKS, they very often, again, they'll either say a reduced fraction or a decimal to 3 decimal places. All right, so we've got 1 out of 4165, which is about 0.0002. If we want to change that to a percentage, that would be 0.02%. So very unlikely to happen. It's very unlikely to get a 4 of a kind. That's why when you're playing a game that a 4 of a kind is a good hand, it doesn't happen that often because it's very unlikely to get. So any type of a 4 of a kind, you only have a 1 in 4,165 chance of that happening. All right, that is it for chapter 4. And so best of luck on your homework. Let me know if anything doesn't make sense. Send me a quick email, or you can use the link in the ALEKS homework, Ask Your Instructor. And I hope you do well on your homework, and I will see you back for chapter 5.